the cost as little as we possibly can and still make a difference, what might that difference be? It could change the search that the tree we looked at, searched through last time. It could increase that tree by exactly one node. So picking too large, now picking as small as we can is also bad. The issue with iterative lengthening searches is that it's tricky to figure out how much you should increase that cost. And there are various solutions with various properties, but unfortunately, that requires more detail than I have time to spend on. So we'll stop here with iterative deepening. And at least you know other variants exist. I promised you a couple details to clean up before we move on to informed search. So I promised you some actual numbers to actually calculate how much more expensive iterative deepening is compared to, say, depth-limited search actually setting a limit. So if we knew the perfect value to set ahead of time, how much more does using iterative deepening cost? Well, we know a limit up to D. We know we have to search the entire, ultimately, we have to search the entire tree down to that depth limit. What did we have to do to get there? We had to search the next smaller tree, the next smaller depth, and then the next smaller depth, and the next smaller depth. We have to search the lowest level in the final tree exactly once, the next level up twice, both at the end and the preceding time. Next level 3, the other direction, we have to search the root node many, many times. As many times as the ultimate depth value we figured out. Next level down, 1 minus that, and 1 minus that. You can add all of that up and compare it. To remember, it would just be this cost, this final cost for depth-limited search, if we actually knew the right limit to set. But if we add all of those up, then we end up with this pattern. For a branching factor of just 2, the overall cost we have to pay is just twice what we would have paid otherwise if we actually knew the limit to use. Not that bad. And as we increase the branching factor, it gets even better. For a branching factor of 3, we only have to pay 50% more. 4, only 30% more. Problems with just 2 choices available at any given node are relatively rare. Larger branching factors we're more likely to see. And for those more likely to see larger branching factors, the extra cost of iterative deepening is relatively minor. Even compared to breadth-first search, that under certain conditions, iterative deepening can actually be cheaper. Why? Consider, back to this example. As I was searching this level, I had to look at this node to figure out I could go to these 2. I looked at this one and realized it hit my limit. It could stop here. There actually is no need to look at these. It already knows that this hits its limit, so it's done. Same here, same here. If this had been a solution, if any of these had been a solution, was no need, and iterative deepening actually would not consider any of these further states that could be reached. But what does breadth-first search have to do in the same condition? As it looks at this state, it has to generate its successors. It has to figure out where it can go to from there and add it to the open set to be considered later. Same here, these have to be added. If it found a solution here, most of the following level, 1 depth deeper, had to be processed, had to be added to the open set. Even though, since it found a solution, they'll never be used. Breadth-first search actually has to do more work than iterative deepening does. Note, however, that this only applies, this reasoning, these numbers specifically, I should say. The reasoning still applies, but these numbers, this difference really only applies in the case where no repeated state checking is done. On the homework, as you play with these, and I'll ask you to look at some numbers of states explored, you'll find that breadth first actually tends to do better than iterative deepening. But that's because of repeated state checking. If you were to disable it, you would find that this property would hold. Because of this vastly lower memory usage, iterative deepening tends to be the go-to uninformed search algorithm when its properties work. So in this case, when you would have used breadth first search, typically you would use iterative deepening search instead. That said, and I just brought it up, we do still have the issue of loops. We talked about, at least with breadth first and related searches, that we could avoid the issue of loops and repeated states in general by using a closed set. And then it didn't cost us all that much, because even though it had exponential memory cost, the factor in front of it was far lower than the general exponential cost of breadth first search. So we could afford to use it, and it would save us quite a bit of time. But we can't do that with depth first related searches. For one thing, I just said, the closed set has exponential memory cost. The entire reason we moved to depth first related searches was to get rid of that. Using a closed set with depth first searches defeats the entire purpose. As well, in addition to that, it also makes them wrong. We already talked about the possibility of exploring a very long path to get to a solution when a shorter one exists. And this exists not only for solutions, but for every node. If we use a closed set to prevent us from visiting a state twice, it's possible we could take a long path to get to a state and never realize, or essentially store that we visited there, then come back later after go far back after we hit our limits and search, and eventually go back and realize there was a shorter way to get there. But we won't explore it because we've already visited that state. And because we won't explore that state, it means we won't explore any long paths that go through that state. If a solution were among those, we wouldn't find it. Using a closed set with depth first, and in particular with iterative deepening, throws away our guarantee of optimality. So we generally don't use it. All is not lost though. I'll come back to that issue. What can we do? At the least, what can we do about loops, if not repeated states in general? But first, there's this issue of exponential cost, in particular exponential time cost. This seems really bad. What use are all of these algorithms if just making a slightly harder problem, a problem that requires a solution that's just one action longer, can cost 2 or 3 or 10 times as long to find an answer for? Just 2 actions longer can cost 4 or 9 or 100 times as long to find an answer. This is really terrible. What good are these? There are many cases where actually that doesn't quite apply. Or rather, we're looking at it from the wrong point of view. That exponential cost comes from looking at it from the point of view of exploring a search tree. But if, for example, we are using a breadth first search and we are using a closed set to avoid visiting repeated states, then how many times can we visit a state? At most once. That's what the closed set is there to prevent, is visiting it more than once. If we know how many states there are in total, how much time do we have to spend? And most of the time it takes to visit each state once. So take our Romania problem. There are 20 cities, 20 states. Do we need to spend an exponential amount of time figuring out how to get from Iran to Bucharest? No. At most, we need to look at 20 things. And then we're done. So this is our other point of view. If we have some idea, instead of thinking about a solution in terms of the length of the solution, if we have some idea about how many states there are in total, then that might give us a better idea of how long we have to spend to find the solution. So not only time, but this also applies, for example, for breadth first and uniform cost search in the case of their memory cost as well. The memory cost for uniform cost search in this case is linear in the number of states. So 20 times something in the case of our Romania problem. Not bad at all. Last issue to cover for uninformed search. We've talked about the depth first related searches so far in terms of our original, our generic search algorithm that had the open set. We said depth first related searches use an open set as a list, and then we add to and remove from the end of the list. In other words, we treat it like a stack. It works, it can be implemented this way, but in practice, depth first and related searches, like depth limited, are implemented recursively. This gives us advantages. Not that the things I'm going to say can't be done, but they're relatively easier to do with a recursive implementation. One of them is that we can reduce the space cost even further. For our generic algorithm, and each state we explore, we have to generate all of the successors and add them to the open set so that they can eventually be removed. But with a recursive implementation, we can generate successors as we need them. We don't have to generate all of them and store them into memory. We can generate the first one. And then think about going deeper, going along a deeper path from that first successor state. And once we've explored all of that first successor in a depth first fashion, then we're done with it. We can throw it away. Now we can generate the second successor and look only at it. That, as I said, now we can generate the successors as we need them instead of spending extra memory to store all of the successors. This can help when we have a large branching factor or when our states are very large. As well, it gives us or at least, again, makes it easier for us to be able to deal with loops. We can't avoid repeated states in general. I already talked about how that would make our answer wrong. We no longer guarantee optimality in that case. But we can at least look for loops. In fact, it doesn't really cost us anything, or nothing significant. Because a loop, to check for a loop, the only thing we have to know is what's in the current path we're looking at. A loop is defined by saying that we want to go to a state that's already in the path that we're currently looking at. If we had a list, if we stored all of those states, then we could check it quickly. And that's all we need, just the states in our current path. Meaning, we only need linear cost for storing all of those states. In fact, it may not even cost us anything. Technically, we're already storing all of those states somewhere because we're generating them as part of our recursive exploration. So in fact, it could have zero memory cost. Or if we want to speed up our checks, is this state already in our path? And therefore, should we skip it? That we may store it in some faster structure, like some kind of set hash table to help speed up lookups. So it may cost us extra memory, but it will still only be linear cost. Nothing significant. Not exponential cost like the closed set would cost us. The homework you can do either way. I'll talk about that more on Friday when I actually talk about the homework. But I just wanted to talk about some of these particular features. Any questions before we at least start a little bit? Not much time left. Start a little bit on informed search. Any questions about uninformed search? Okay. Well then, you'll recall the uninformed search we've talked about so far, we also call blind search, because when we look at what it's doing, it's essentially, it is stumbling about blindly. It's just trying everything it can, moving every direction it's possible for it to move, until eventually it finds a solution. This is, in a way, dissatisfying. So when we think about trying to solve a problem like our Romania problem, then when I ask a human the question that we're trying to answer here with search strategies, from Iran, those 3 cities we can move to, which should we look at first? The answer is obvious to a human. Looking at the map, they know among the 3 that Sibiu is the one we should look at. If you ask them why, the explanation will be some version of, well, it gets us closer to Bucharest, where we're trying to go. But that's not information that's in our basic problem definition. There's no idea of closer in our successor function, of closer in our cost function. Our cost function only doesn't talk about closer to our goal, it talks about what did it cost us to get here. That's extra information outside of our problem definition that we humans use to solve this problem. And that extra information is what lets us solve it in what we think of as an intelligent manner, of having a good idea of what the best thing to look at is. And so informed search, we will put in those same terms. We'll try to make it use some extra information in that fashion to not only find a solution and find an optimal solution, but hopefully find it while exploring as small of the search tree as it possibly can. The algorithms we'll talk about will generally fall under what we call best first search algorithms. They'll use some type of evaluation function to describe a good option versus a bad option, and then select, based on that evaluation, whichever one looks best at any given time, hence the name best first. By some evaluation of best, always pick the best one. Again, so ideas about best. And we'll have various ideas, and in fact, the algorithms that we'll talk about, greedy search and A-star search, only differ in that idea of what it means to be good, what the best thing is. And actually, the difference will really only be relatively minor. Because we're not talking about a number, and we want to choose a state based on a number, this is starting to look a lot like uniform cost search. We had a number, a cost assigned. We wanted to choose the cheapest thing so far to look at first. So we used for our open set of priority queue. And we'll do the same here. It's just where with uniform cost search, the value that it was keyed on was that cost, the path cost. Now it will be the value of this evaluation function. What do we use for that evaluation function? For the first, that we'll start from, and we talk about it because it will lead us to our, in a sense, our ultimate search algorithm, A-star. Greedy search, for its evaluation function, uses what we call a heuristic function. It's a function that estimates the cost that we have remaining. So remember, the path cost function talks about how much did it cost to get from where we started to where we currently are. Heuristic tells us how much do we have to pay to get from where we currently are to where we want to be. Okay. Having this value, if we know the cost that it would take us remaining, then it makes sense. What should we choose first? The thing that gets us closer to our answer. For example, we want to get to Bucharest. Say we have two options we have to choose from. We have to choose, should we look at Fagaris next? Should we look at Protesti next? From these two options, Fagaris, we know we can look right here, it tells us it would cost us $211 to get to Bucharest. It's really far away. Compared to Protesti that only cost us $101, it's quite close. Which one seems more promising? Protesti. Makes sense. And this is the same reasoning greedy search operates from. Always choose the one that gets us closest to our goal, that leaves us the least remaining work we have left to do. And this could work if there weren't a catch. Because there was one other part of that heuristic.